right. How's everyone doing? My main objectives for the day are we're going to review the last couple things in Chapter 7 we talked about. I'm not actually going to introduce anything new to you guys today because I want to spend at least some of today looking over the test review stuff that I posted, make sure you understand all the things that are there and everything you need to be able to do before the test. So today will be half Chapter 7 review, half test review. Any questions, concerns, etc. from you guys? Anything at all before we get started today?
How do you calculate impulse? What's the formula?
Impulse is change in momentum. So I'd say the formula has 4 parts to it. And really, you could just pair any of these two together to make a short formula. The definition of impulse is the change in momentum. So if something's momentum is changing, it has undergone an impulse. If it loses 5 kilogram meters per second of momentum, then its impulse is -5 kilogram meters per second. So impulse is literally just a specific word for the change in momentum. And there's at least 3 ways to calculate it. My preferred tactic is typically mass times change in velocity, because whenever something undergoes an impulse, mass does not spontaneously change by itself, so usually what will happen is the object's velocity will change. So mass times change in velocity will tell you the change in momentum, and therefore the impulse. The last part of the formula is just pointing out that force is what causes the change in velocity. Force is what causes impulse, and typically, the bigger the impulse, the more force is involved. So that's just what the last part means. All of that is on the equation sheet that I have recently updated. Right there under impulse, the whole thing I just put on the board. You will have access to this formula sheet on the test. Whether you print one off yourself or not, I'll have a stack of them in front of everyone to use. You should also bring a calculator. It can't be your phone. It doesn't have to be fancy. It just has to be able to handle square roots and squares. Anything else on your mind? Here to start. All right. And for the first thing, let's work very briefly on some Chapter 7 stuff. I'm not going to do anything new. Just want to practice the last couple of things we talked about. There's a few concepts from Chapter 7 that we haven't gotten to yet, just because it took longer than I expected. And so I'm just going to postpone those to after the test. The last couple things would be power and efficiency, but we'll do those either next Friday after everyone's taken it or the week after that. The homework is already divided up. The Chapter 7 homework is divided up into which parts are on the test and which parts are not. So the parts that are not on the test we haven't covered yet. There's like 4 of them. We'll get to those next week. For the parts that are on the test, to review the last couple things we talked about, we looked over the concept of work, the idea that when you exert force on something, you are using up your own energy and giving that energy to something else. So work is the use, transfer, or transformation of energy. Anytime one of those things happens, it's because something did work on something else to facilitate it. So work is the mechanism through which energy is used, transferred, and transformed. And again, you do work every time you exert force on something and make it move, which is why every time you exert force, you use up energy and eventually tire yourself out. The one caveat to this formula is just that the force and the displacement need to be parallel to one another. If I push something to the right and it moves to the right, I did work, I accomplished the task. If I push something to the right and it moves up, odds are something else is doing that and I'm not the one accomplishing anything. So I didn't do any work in that case. Questions on the principle before one quick practice problem? Bless you. All right. So, just to summarize the math, we're going to examine an athlete who is able to deadlift something with a mass of 75 kilograms, which, again, if you're not used to thinking in grams and kilograms yet, is a lot. That's possibly a whole adult human. Lifting the weight a total height of 2 meters from the floor. So, starts on the floor, then lift all the way up here. The two things I'd like you to tell me are how much work is required to perform this feat, and then separately from that, how much GPE does the weight gain as it rises from the floor up to 2 meters? I'm going to give you guys a couple minutes to ponder that, possibly work with each other, and tell me these two numbers.
joules.
Yes. Just gonna write that here. That is the most accurate answer, correct. Remind me, everybody, what is now if you got 1500, that's fine, I just need to use 10 for gravity instead of 9.8. And
Okay.
I'll grade either correct. If you use 9.8, that's more right. I would give you the points for that, obviously. Ryan, what's the formula for work?
Mass times acceleration times height.
Yep. Force times displacement. That's the work formula. Mass times acceleration will be here in a second. And I'm writing delta y instead of delta x just because the object is being lifted vertically. We're lifting upwards. Displacement points up, force points up, so the parallel thing isn't an issue. We know the distance upwards we're going. My question now is, how much force does it take to lift a 75 kilogram item?
Newtons?
Yes, but not quite. To lift anything, in general, how do you know the force required to lift it?
Are we talking about in general? or-
In general. To lift anything up, about how much force do you have to exert? More than, or in this case, more than or equal to what it weighs. You need to know the weight of the item, because to overcome gravity, you have to at least equal it before the object will start moving upwards. So the force needed is the weight of 75 kilograms. And how do you find the weight of something on planet Earth? Which is?
Isn't that mass times acceleration?
Mass times the acceleration of gravity. Correct. Fg equals m times g. G is the acceleration of gravity. In this class, we've been using 10 for that, but 9.81 is more accurate. So 75 kilograms weighs 750 newtons, or if you use 9.81, slightly less than that. So that's the weight of the item. Therefore, you have to exert at least that much force to lift it. So that's the force that we'll use over here. 750 times 2. They are parallel, so that's fine. And you get 1,500 joules if you use 10 for gravity, or 1470 if you use 9.8 for gravity. I would accept either on the test.
So it's the same for both of them?
Yes, good observation. How much GPE does the weight gain on its way up? Formula for GPE is mgh. So we take the mass, and multiply it by g again, multiply it by the height, and, well, that's funny, it's the same number. That's on purpose, by the way. It's the same number because of the conservation of energy. If you do this much work on the item, it's gonna gain that much energy, because this is the energy you are using up and sending somewhere else when you do work. That energy can't be destroyed, so now it enters the barbell in the form of GPE. Energy was conserved. So, when you're doing work opposite gravity. The force you have to overcome is the force of gravity. So keep that in mind if you're ever calculating the work of lifting something. The force will be the weight of the item. And when you're lifting something, the work you're doing is giving the item GPE. The work done will become GPE in the object because of the conservation of energy. How's all that feel? All right. With that said, that is the last thing from chapter 7 that will be on the test. There is 2 more things within this chapter that we'll cover later, those being, well, maybe 3 if I include the work done by friction. The other 2 are power and efficiency. Again, we'll do those later. I need the first test to happen next week, so I'll just cut off the content there. To that end, if you look at the homework assignment for chapter 7, I note which book numbers are not on test 1. Those are the power and efficiency problems that you don't have to be able to do with the test. And in turn, if you look at the, bless you, document version, I further have them separated into on test 1 and not on test 1. Just to make sure you don't get those mixed up while studying. So, before switching gears and doing test review stuff, any questions from the parts of chapter 7 we've talked about? All right. In that case, my plan for the rest of today is making sure you've heard from me everything that you need to know and be able to do before you take the test next week. As a reminder, test will be given during lab time in this room on those 3 days, the 19th, the 20th, and the 21st. So when you would normally go to lab next week, you instead come here. There is no lab at all next week. You're taking the test instead. You will have 3 hours to take a 1-hour test. So you don't have to rush in and worry about finishing it before going to another class. You'll have a formula sheet, you'll have a calculator, and you will have either me or Dr. Edwards at the front of the room to ask questions. Either he or I will make sure that you absolutely understand what is being asked of you and that everything within the question is clear and that you know what you need to be doing. So do ask questions, that is encouraged. Now normally I don't let students jump between labs each day of the week because there's a certain limit on group size and the number of chairs that are in the room, in the actual lab room, but this classroom doesn't really have that restriction. So if one of the days that you don't attend lab fits for your schedule and you'd rather take the test on that day, you're allowed to just show up then. If you have Monday lab, but your Wednesday's free and you just want to do it on Wednesday, you can. You don't have to email me, you can just show up. This is only for the test version. Don't just show up to a different lab. Well, does that sound fair? Okay. And to help study for the test, again, you should be doing the homeworks. They are basically the practice test. Within each chapter, the number of questions, the list of questions posted here is the list of stuff that you should know and be able to do before you take a test or an exam on that chapter. To help specifically with the test though, I have posted additional practice questions. I usually do this for my tests and exams because some students always ask me for more, so I post some. We have a test 1 tab. The tab itself has a study list. We'll look over that in a minute. And posted beneath that is Physics 1000 Test 1 additional practice questions. If you want one thing to specifically focus on to make sure you are ready for the test, I would recommend this. I wrote the test and then I wrote this to make sure that it's on the right topics. Do note though that there is this blurb at the top that says, note, I make my extra practice questions harder than the actual test because I'd rather you make mistakes here than on the test itself. What I mean by harder is there's more of them, there's more study questions than there is test questions. And for example, this first page is just concept questions. There's multiple of these. And here, I usually just leave you space to write out a sentence or two about whatever I ask, and then you can compare that to whatever I post on the answer key for it. On the actual test, the questions are written such that they usually only take 1 or 2 words to answer. So this is harder in that I'm asking you for more information, but on the test it'll be, is this present? Yes, no. Is this in equilibrium? Yes, no. Are these third law pairs? Yes, no. Just because I want you to be able to do them quickly and not bog you down having to write out a paragraph. So if you can do the practice test, you'll be fine on the test, absolutely. Again, this is longer on purpose. The actual test is 12 or 11 questions, I don't remember. Each a combination of math and very short answer. First page is a bunch of concepts that you should be familiar with, and then several math questions to follow on the following pages. Each of the proper test questions is kind of a multi-part thing. Like I might describe a scenario, ask you 1 or 2 one-word answer concepts about it, and then ask you to calculate something within that scenario. So the formatting will look kind of similar to these. I will give you a prompt, ask you a couple things about it, give you space to work and put your answers. I would consider this additional practice in addition to the homework. I wrote the test in such a way that if you've done the homework, that will massively help you, because a couple of the test questions literally came straight from the homework or are slight revisions of homework questions. And I then also, again, wrote all the practice questions after writing the test to make sure that all the skills in math and concepts are the same across the two. For example, practice test says list Newton's 3 laws of motion. On the actual test, I've been saying this all semester, you do have to be able to pick them out of a lineup. I give you 5 statements and you label which one is Newton's laws and put the correct number on them. 2 of them are not Newton's laws, you leave them blank. So again, I'd say this is the harder version in that you write them versus, pointing at them and labeling them out of a list of pre-written statements. I feel like I'm repeating myself. How do you guys feel? Yes?
Is there like multiple questions for like each question? Like is there like multiple steps? Sorry.
Yikes, I apologize. Most questions do have 2 or more parts to them. Again, I would show how I format a couple of these questions. I think number 4 here is a pretty good example. It's got 4 parts to it, but each part is kind of meant to go rapid fire in the logical order you'd think about them anyway. Like 4 describes a car driving at constant velocity. Gives you that velocity, bless you, tells you the mass of the vehicle and the force pushing the engine forward, pushing the vehicle forwards. And then 4 questions mixing up concepts and math. First, what is net force on the car? Just one quick number. And the secret to this one is, car is driving at constant velocity. What would that make the net force? 0, very good. Then B, is the car in equilibrium, given what you just said a second ago? Yes, because the definition of equilibrium is net force equals 0. So I try to write them again in a logical order that you'd be thinking about it anyway. C, then identifying all the forces that are acting on the vehicle. You've already determined that they all add up to 0, so then I think about it in terms of drawing a picture, because I have a very visual brain. figuring out which forces are pointing in which direction such that they do all add up to 0. You've got the weight down, normal force up, the engine forward, and there has to be something pushing backwards, and that would be friction. We've already determined that they all add up to 0, you're just figuring out what has to be here to make that true. And then the last question would be, how much kinetic energy does the car have? Use the formula in conjunction with the two relevant numbers there. So, they are mostly multi-parters, but again, I try to write them in a helpful order, if that answers the question. I do include space for math, and I also include lines that I'd like your answers written on, just because if they're in a certain spot, it helps me find them, and then it makes the grading faster, which I appreciate. By the way, once I am done grading them, I will give you your test back. It is your copy. You get to keep it because it is good study material for the final exam. So you will not only know your grade, you will have the paper. Any other questions about this thing? I'll be posting an answer key for it this afternoon, by the way. Yes. Yes. Because the drawing would then have all the forces, and then I just ask you to put numbers on them. Yeah, I like pictures. I like free body diagrams. Sometimes I ask for them.
So if I draw that,
All right. Additional study aids. This document is loaded within the Test 1 tab. If you click on the tab itself, we have a list of all the concepts that you should know for this test. They all blend together, and often one question will involve multiple of them. Like any question about force is gonna involve the laws of motion, for example. So just because there's like 20 things on this checklist doesn't mean there's 20 separate test questions. You should treat this like a checklist though. You should go over it, make sure that you understand the concepts, how we use them, any formulas that are relevant to them. And I just kind of want to briefly go through the things you should be thinking of when you look at all of them. First thing was units. You need to make sure to do metric prefix unit conversions. I don't think I actually gave any like unit to unit conversions. There's no feet to meters going on this test, but there is grams to kilograms. You do have to be able to do that. So, how many kilograms is 10 grams?
0.01.
0.01, excellent. Oops, I almost wrote it wrong. And to help with that sort of thing, you can write that on your formula sheet.
how does that work again?
So this stands for, in order, kilo, hecta, deca, base unmodified, decicenti-milli. Up here, this went from the base unit to kilo. And so to use this, base to kilo means you drag the decimal point 3 jumps to the left. Also, when I say units, I do want to point out that I do want units on any numerical answers. I don't put a lot of points towards that, like maybe half a point out of a 10-point question is just units on your answers. But I do want them to be there because if you were being a professional scientist, you do have to note the units that your work is in, because when you don't, you get situations like when NASA slammed $1 million rover into Mars and then it broke and then we never got it back. Because one guy was working in meters and someone else was working in feet. True story. So, put units on your answers, be able to do metric prefix conversions. Next, laws of motion. Again, you have to identify them out of a lineup, and then understanding them does help all of the math and concepts to follow. Quick summaries here. First law is inertia. If at rest, stays at rest. If in constant motion, stays in constant motion until acted upon by an outside force. Second law is net force equals ma. If net force is 0, you have no acceleration. If net force is not 0, you have acceleration. And third law, action reaction. For that one, you do have to be able to identify third law pairs, at least to a small degree. Main thing I'd point out about that is, quick sample, this is a 1 kilogram weight. What two forces are acting on it right now? Gravity down and
The force of the table.
normal force up, very good. Are those two things third law pairs? No, very good. Why are they not? There's at least two reasons. They're both acting on the same object. Third law pairs cannot act on the same object because they follow an if A on B, then B on A structure. There's two separate targets. But in that case, I'm pointing at the weight, they both act on the weight. Normal force up, gravity down. Two things on the same object, that's two forces, two things acting on a third thing. That's not ABBA structure. So that disqualifies it automatically. Another couple of reasons if you need a different one to help remember it. Normal force and gravity are not always equal and opposite. There are times normal force points this way if the surface is sloped, because normal force is always perpendicular to the surface creating it. If they're not opposite, they're not third law pairs. And they also aren't always equal, because if I push harder down on this thing, the normal force increases, but its weight doesn't. Its weight is a function of what's going on in Earth's core, not what I'm doing here. So, normal force and gravity are not third law pairs. What is the third law pair to gravity? More gravity, correct. If Earth's gravity pulls down on that weight's gravity pulls up on the Earth. It sounds silly, but it's true. Different question, what would the third law pair be to the normal force of the table pushing up on the weight? If table push up on weight, therefore weight pushes down on table. Table doesn't care why, it just cares that it's happening. It doesn't know or care if gravity is responsible, it just knows weight push, I respond. So, be able to do that sort of a thought process if I start asking about action-reaction pairs.
So when we would have to do like the free body diagram in this test, would we have to put like all 4 of the reaction pairs, or just put the gravity in the middle?
If I asked for a free body diagram of the forces on that object, it would just be the two. Because the pairs to each of those are what it does back to the other two things. Those forces aren't acting on it, therefore they are not on the diagram of forces acting on it. Does that make sense? Okay. Next concept related to force, you have to identify equilibrium states, which is to say, know if something is in equilibrium based on its motion or based on the forces acting on it. Quick sample question. Well, is that object in equilibrium right now? Why is it in equilibrium right now? I think I heard two correct things overlapping, but my brain couldn't process them both. It's at rest. If it's at rest, it's not accelerating. If it's not accelerating, I'll put this list of thoughts here. If acceleration is 0, then net force is 0. And equilibrium. Is the two qualifiers for equilibrium. Acceleration is 0 because net force is 0. Can you be moving and be in equilibrium?
Yes.
Yes, you can be moving and net force be 0. It just means you're moving at constant velocity. Is this equilibrium? No, why? Because falling is accelerating. Very good. Similarly, that's also on this list. Falling is an acceleration. Be able to use G equals 10 meters per second squared on the test where applicable, or 9.8, your preference. Acceleration kind of pairs back into the next thing here, one-dimensional motion, displacement, velocity, and acceleration. Main thing about that is, if you look at the updated formula sheet in the resources tab, be able to use these 4 formulas to describe an object's motion: its displacement, its velocity, and its acceleration. Questions so far? About halfway through the list. Bless you. All right, acceleration of gravity, again, G equals negative 10 meters per second squared or negative 9.8. I would accept either. Forces ties back into the laws of motion, but just to make sure to define some specific forces that you will be seeing. Force of gravity, again, on planet Earth, this is how you find the force of gravity on something. Weight is a synonym to force of gravity. Mass is not a synonym to force of gravity. Mass and weight are separate. If I ask you for weight, this is how you find it. If I ask you for weight and you write kilograms, I'll be upset. And then normal force, again, a response to a surface being pressed into. And friction. Main things to note about that are friction opposes motion. So if I'm moving forward, there's a force of friction pushing backward. And static friction doesn't come up the way that I wrote the test, but kinetic friction does. Thing to remember about kinetic friction is it doesn't increase. If you are moving and there is a force of kinetic friction, that value does not change as long as you are in motion. Doesn't matter if you speed up, doesn't matter if something else pushes harder forwards, the friction backwards stays the same. But friction backwards often shows up to make sure that, to try to stop forward motion. Next couple entries are the things we covered last week and this week. Everything in blue is from chapter 6. Be able to calculate an object's momentum. Be able to calculate an impulse if its momentum changes. The main thing to remember there is just, again, impulse is the change in momentum. It's just a specific term for that. Remember that momentum is conserved in collisions, even when it looks like it isn't. That does include dropping something on the ground. The momentum just transfers into the ground, and the earth is too big to notice the motion of. And again, applying this to collisions, total momentum involved in a collision remains the same before and after. It is just distributed differently between the two items. I remember from lab this week, cart 1 approaches cart 2, cart 1 brings momentum with it, and afterwards they share it. Does that make sense? There are practice questions for that in the homework and on the practice test. All right, and then lastly, the stuff from this week. Talked about energy, namely 2 specific forms of it, kinetic and gravitational potential. Those are the only 2 types that you'll have to calculate. But you should be able to identify when something has each of them. It has KE if it's moving, it has GPE if it is some height above a point it can fall to. Energy is conserved, it is not destroyed, nor does it spontaneously come into existence from nothing. If something gains energy, that means it either already had it in a different form or something else is giving it that energy. Again, kind of like the lifting thing question we did earlier. The GPE it gains came from the work that the person does on it. So all of the energy is always accounted for, even if it's in a different form. And lastly, work, the act of using energy when you exert force upon something. How do you guys feel?
Great.
Yay. That's the full checklist of concepts. If it's not on that list, it's not there. Question?
Yeah, when calculating so I know you have like the force of gravity and but because it's negative, you just like change it to positive
They
weight?
can be down.
So the weight, the force of gravity does point down, so that does inherit the negative. As it relates to what we did earlier. When we were looking at the work required to lift something, this force that we used is equal in magnitude to the weight, but this is technically a different force, because this is the force you are exerting upwards. So if the weight is negative 750 newtons, you would have to exert positive 750 newtons. So that's the reason why the negative that does technically exist would vanish when we did that calculation. Does that answer the first question? Or does that answer part of the question? Okay. I try to be consistent about the negative, because the acceleration is always down, weight always points down. This is one of those times where that negative goes away because, again, this is a separate upward force that happens to be the same number. This is just one of those cases where the negative kind of gets ignored, if I'm being honest, and that has to do with vector math. Within this formula, two vectors get multiplied together. G points down, H points up. And when you multiply vectors like that, the direction just kind of goes away, depending on how you do it. And that relates to the fact that energy isn't a vector. Energy doesn't care about direction. And so, bless you. For that reason, and because of this multiplication, the negative sign does just kind of vanish when you use it in here. And in fact, I should have done this on the formula sheet. You can absolutely, if it helps you remember that, put absolute value brackets around the G and the GPE formula. Well, normally G is negative 10 meters per second squared. So normally, if you put negative 10 in here, you get a negative GPE, but that doesn't really make any sense. Because if you are elevated, you have GPE. Energy is not a vector. It doesn't care about the direction. That means it doesn't care about the negative sign. So if you want, and this is only if it benefits you, you could think of this G as having absolute value brackets around it. Absolute value being you just take off a negative sign if it has one.
So, but, okay, so like if you calculate weight, is it negative?
Yes.
If you just, so it's always negative?
Yes,
Cheese.
I would, in my own work, consistently say that weight is a negative vector because it points down.
So our value for weight should
Yes. I don't know if I would take off on that on the test if you didn't do it, but I do like that consistency. That's how I try to be consistent about that in my own work.
Okay, but over there you put 10.
Um,
Like when you
Oh,
calculated it.
You're right, I did. I was kind of trying to brush past the fact that we weren't about to put a negative in here.
Okay.
So I kind of skipped it for that reason. There's a lot of physics that I know and do subconsciously, but that like this class is not about the way that my brain does physics, it's about the physics that you guys need to do. So sometimes even though I would know this is negative and then this is a different upward force, I just kind of skipped it to try to not spend time explaining it, or not try to confuse you guys, and I apologize. Technically, since this is a force of gravity, I'd say it points down, and for that it would be negative. And then the force in this calculation is a different positive version, because this is meant to represent the force we exert upwards that is equal in magnitude but opposite in direction. Is that?
Yeah,
Oh.
I was just confused if we would keep it negative because of this.
No, I'm glad you pointed it out. I did kind of skim that earlier, so thank you for mentioning. Anything else on your minds right now? All right. Again, if you can look over everything on this checklist and feel comfortable, if you can do the practice questions and feel comfortable, you will absolutely be all right for this test. Please let me know if you have any questions, issues, etc. while studying. Question?
Yes, sir, I'll wait.
Okay. And please have a wonderful and restful weekend.